Hello, everyone. Glad you could all make it. As I mentioned, my name's Stuart Barnes. I'm a sales engineer here at Undo. And today, the topic that we're going to discuss is how best to catch and resolve defects and bugs in your programs using the Undo debugger, UDB. So without further ado, I'll jump straight in. I guess I'm going to start with a truism, which is basically that software will fail at some point. I guess we're all developers here and we've all had that experience. Application failure is inevitable. And in fact, the only uncertainty is the way in which it will fail. We do know that it's going to fail in some new and unexpected and infuriating way. So, as developers over time, as we gain experience, we come up with new and effective strategies to tackle that specific problem. And certainly one of the things that we do when we're trying to solve a problem or solve a bug or a defect is to collect sufficient information that we can put together some kind of hypothesis of the problem and allow that to guide us to the root cause. And as experienced developers, that's the way that we tackle these problems as quickly as possible. But obviously, any tools that we can use to help us with that are always welcome. And whether that's tools which help us collect information or tools which help us actually get to the root cause directly, that's all good stuff. So probably worth saying, that even though you all know, I guess, that debugging takes up way too much of our time. We spend more time debugging than we would like to, because obviously debugging is hard and it can be a time sink. And we'd all rather be implementing new features rather than debugging the old ones. So from a developer's point of view, it's a huge drain on your productivity. It adds pressure to your timelines, and you really want to get to the bottom of any problem as quickly as possible. From development manager's point of view, obviously, trying to get releases out of the door, having to debug things, new or old problems is again a drain on resources and a drain on productivity, and puts release cycles at risk. So trying to get to a good point in your application is extremely important. So how have we been doing this in the past? We have some sort of conventional ways of collecting that information that we need to use to solve bugs. And the main three are kind of logging or core dumps or debuggers. And these are all pretty effective ways of collecting that information, but they all have their downsides. So if we take logging as the first example, or printf debugging as we informally call it, we're trying to predict the type of information that we need to solve bugs when we put that logging together. And necessarily, we're trying to figure out far into the future what information we'll need to capture. But by their nature, bugs occur when we encounter something that we weren't expecting. So quite often, the logging information that we're able to capture doesn't really reflect the actual situation once that bug has been encountered. In those cases, we often need to re-instrument, maybe send a debug version out to the customer if it's that kind of relationship, or at least, very least, we have to try and rerun the test case, and hopefully the bug will reappear, but this time with more instrumentation and more information. And of course, that's all good, providing that the problem isn't sort of flaky or intermittent. Another way of collecting that information is through core dumps. And again, core dumps are a great way of collecting a snapshot at the end of the run. And that really shows us, a lot of what we need to understand what happened at that point. But what it doesn't tell us is what happened prior to that point. So core dumps are useful, but are limited. And of course, if your problem is not a catastrophic failure of your application, but really just some sort of divergence in behavior, you may not get a core dump at all. So again, they can be limited. Of course, the final tool in the arsenal is an interactive debugger. And certainly this is the most hands-on solution, but it can be time consuming to get to the root cause of the problem, not least because you have to use what we term an iterative strategy a reverse iterative strategy to get to the bottom of things. So, you would normally inch your way forward very carefully, not go too far forwards, because once you, hit that bug again, you effectively lost your application state. You then have to make a note of where you got to and then restart the debug session. And again, if you have problems recreating the bug, if it's an intermittent fault, then that's going to be very time consuming. So these three methods are certainly useful, but they have constraints which can make getting to the root cause difficult. So how else can we approach these sorts of problems? And certainly the strategy for finding root cause is really all about finding out what just happened, what happened just before this point of failure. And certainly there's a sort of famous quote from Kernighan and Pike, who they liken it to a murder mystery. You have the end result, you have the body in front of you, and you need to somehow get back to the point at which that body was previously working, and get back to the reason why the defect in the software has occurred. And to that end, we have at Undo a strategy that we call software failure replay. And that tries to support that natural, looking into the problem of working backwards from the point at which the error has occurred, and really going back in history, going back in time, so that we can understand exactly what the application did to get to that failure point. So Undo's technology implements, as I mentioned, a software failure replay capability. And the way that we do this is through a recording of the application. So the application is, we attach the application with our debugger, and the debugger at that point starts recording every event that occurs in your application's history. And it will do that all the way to the point at which your application fails. This means that you have essentially an event log full of everything that your application did. And of course, once you have that, you can then go backwards through that event log, basically undoing everything that happened before, till you get to a point in your program's history where you can recognize a change in the application state which led directly to the problem. Effectively, you can then resolve the problem there. So I have a demo that I can show you, and you can see this actually in action. So this is a relatively short demo, and it's going to take really a very simple problem, but it's useful to show you this just so you can see the type of strategy or workflow that Undo's technology helps you implement. So I have a really simple program, which I'm just going to run for you. Essentially, it's just calculating a bunch of square roots and then caching those values, and then when the time is right, returning values from the cache to speed up the whole proposition. So let me just run this short application. So you can see it's given us a little bit of output. It's given us some logged information. So this is pretty typical of what you would see in your own applications, I guess. And then when we've got to a point where the application is having a problem, it's also tried to dump out some information to give us some idea about where the application's gone wrong. So in this case, it's given us some indication of a problem in the internal state, and given us some indication of where it thinks that problem has occurred. And then additionally, we've got a core dump here. So at this point, there's no Undo technology involved. This is just our application failing. So what I can do is take our debugger. In this case, we're using C-line as the front end, but UDB is really a drop-in replacement for GDB. So in a lot of cases, certainly if you're comfortable with the command line, you can use UDB in exactly the same way as you can GDB. We do support some IDEs, so for example, CLion, some Eclipse, any Emacs users out there, we're very integrated into that. And we have some other stuff on the horizon, such as VS Code. So, we're trying to support as many IDEs as possible, and certainly that helps with visualization. In this case, we're using CLion. So I have my application. I've got my source code in the source code window, and what I'm going to do is just kick off a debug run. So let's do that, and you can see, hopefully in the window below, that we've got to a point, okay, where we're I've set a breakpoint at the start of the application, so we can step through. So I have then typical debugger type commands. So I can step over just in normal GDB style or normal debugger style. And you can see we're stepping through the application one instruction at a time. But the reversibility of our debugger, so basically, as soon as we started executing this application within the IDE, UDB has started recording that application, and it started recording all of the events, all of the changes in application state as we progress step by step through the application. But what that does mean is we can go backwards. So, and as we go backwards, we're also able to examine the application state at any point. So we can look at values, in the variable window at the bottom. We can get a pop-up to give us instantaneous values of variables and so on. And, we can move backwards and forwards as we need to. And, I mentioned earlier about about education. This is a great way of really understanding what your application is doing by going backwards and forwards. And this is great for, if you have people who are not new developers, maybe not sort of au fait with the code, or if you have legacy applications where you haven't, where the original developers have gone, then just being able to go backwards and forwards and examine what the application is doing, even outside of a defect, is a very educational capability. So what I'm going to do is I'm just going to run this application to the end. And of course, this is something that you wouldn't normally do in a debugger, because once you hit that that failure at the back, then you'd normally have to restart the debugger and do the whole thing again. But let's go ahead and do that anyway. So you can see now that we've reached an assert. We can look at in the bottom left, we can see the stack trace, and we can see that we're some frames into the assert function. So we can now unwind the stack by essentially stepping out of each frame. So this is different to using just up and down commands in GDB. This is actually executing backwards and updating the application state accordingly. So let's do that a few times until we get back into our main source code. There we go. And we can see now that we're in this conditional block. And the reason why we're in there is because the returned cache value is not equaling the expected value. And at this point, we can, again, step backwards and try and understand why that is. And we know just from inspection that the square root underscore cache is calculated in this, this function up here, cache calculate. So we can step back and then step into that function. So let me get to the return point. Okay, so now we can see that the value being returned here is 0. So that matches with our failure mode that we saw earlier. And really the question then is that we know that this value that's been returned here is incorrect. The array represents a memory location. So the question at this point would be, well, how can we look at the last time that this memory location was updated? Because the last time it was updated incorrectly. So the way we normally do this in a debugger is to set a watch point. So that's what I'm going to go and do here. And just to mix it up a little bit, I'm going to drop into the GDB's or UDB's command line and just do it from here. So so we know that the variable name is cache .square root. I can set that watch point. And then I can go to, on the left-hand side here, reverse resume. And what this is going to do is continue backwards in a reverse execution to the point the last time that that particular memory location was updated. So let's go ahead and do that. Okay, so we can see now, if I look at my variables, local variables, that I've got to a point where that memory location was indeed updated. And we can see that it was updated with some strange numbers. So basically, the value there in square root 2 is this huge, huge number. The reason why it's not 0 is because, well, once it gets cast into that cache array, it will overflow and be turned into 0. But for now, we've got this odd number. Obviously, something's not quite right. And if we look at the value here, we can see this is calculated up here just by inspection on line 45. And if we take a look at what's going on there, we can see that we're trying to take the square root of a -1. And in fact, that is the root cause of our problem, essentially. And again, by inspection, we can see the reason why we're trying to take the square root of -1 is because in this loop, we haven't done any boundary checking. So you can see that we are able to go from the essentially the failure point right at the very end. We have got to the end of a stack. We can rewind that stack trace back to a point in our code where we can start examining the internal state. And then once we've identified the particular part of our application that's failing, we've been able to set a watch point there. And that really gives us an opportunity then to reverse continue right back until the point at which that memory location was updated, and then we can get to the root cause. That's a pretty typical workflow, but the technology does allow you to do any number of other things. For example, if we'd found that the stack, when we resumed, had actually, instead of showing useful information, had been somehow broken. Again, we can still reverse back step by step and unwind that stack until we get to a point where the stack is again readable. So the entire application state is maintained within that that recording file, that recording essentially in the debugger, and you have total control. We often liken it to going backwards and forwards in a DVR. You can scrub backwards, you can scrub forwards, and you can really see, what's happening at any given point. So hopefully that gives you some idea of, the typical workflow that you might use and how you can use the recording technology in UDB to get to the root cause of a problem. Okay, so I think if anybody has any questions, then more than happy to answer them now.
Thanks, Stuart. We had a couple of pre-submitted questions. Mm-hmm. So while we're just waiting to see if anyone has any others, I'd like to just run through a couple of these that might be of interest. One question that we had from an attendee is, what other IDEs can, actually, I think you covered that, actually. That came in just as you were running through. So we covered which IDEs we cover, but what's the main difference between UDB and GDB?
The main difference between UDB and GDB is effectively the reverse capability. GDB does have a reverse capability, but it's woefully slow, and in fact is effectively unusable. So really where UDB shines is that its reverse capability is super optimized. It's very quick and allows you to really get into the, get to the nub of the problem in very short order. But apart from that, in terms of usability and in terms of the commands and so on, it's very, very familiar. So if you're a GDB user, certainly a command line GDB user, then you're going to feel right at home. Really, the big difference is that there are a bunch of reverse navigation commands that have been added. And that works both at the kind of source code level, where you saw I went did a next and then a reverse next, continue and reverse continue. But also we have a lot of thread specific commands which allow us to move through specific threads as we need to.
That's great, thank you. Another question, this is really interesting actually. Can UDB handle multi-threaded applications or applications with shared memory?
So yeah, the answer to that in both cases is yes. I think like I just mentioned, we have some thread specific commands which allow us to sort of dive into what each thread is doing in an application. And we can make use of GDB's existing thread specific commands, setting breakpoints and so on. So yeah, multi-threaded programs, not a problem. We do serialized threading. The reason we do that is to allow us to ensure the ordering of threads remains the same. So as we go backwards and forwards, we're getting the same behavior. That in general is not going to mask concurrency issues. We still see, if there's a problem, if there's a race condition or a deadlock in your application, then we're still going to see it. In terms of multi-process, yeah, we can certainly do that. Generally, we're going to be really recording only the process which you're attached to, if you see what I mean. So if you have an application that has multiple processes, just like any other debugger, you're probably going to have to attach extra sessions, extra UDB sessions to each of those processes to understand what's going on. But yeah, certainly we handle both of those cases.
Okay, and Amit Kumar, thank you so much for submitting a question. Amit has a question which is, does UDB support all its functionality through command line?
Yes, it does, or it can, yes, certainly. And that's the, I guess that's the native interface is the command line interface. So I think I tried to sort of mix it up a little bit there. If I just go back by setting the watch point. Funnily enough, C-Line has a slightly odd way of implementing watch points. So that's one of the reasons why I jumped into the GDB prompt. But you can certainly do any of the GDB. You can issue any of the UDB commands on the command line. So if I just give you a oh, okay, it's not going to let me do. I was trying to do a tab complete. In a native GDB interface, it'll actually show you all the UDB commands if you hit the tab. But yeah, basically, for every forwards command, there's a corresponding backwards command or reverse command. So that way, we're able to try and keep the interfaces as intuitive as possible on the command line.
That's great. Another question from Michael Winkler. Thanks, Michael. Is there any plan on introducing reverse until line number similar to the until line underscore number? Is there any plan to introduce that?
That's a good question, actually. I don't know the answer to that. I think we have implemented. Let me see. Yeah, I don't believe that we have a specific command to do until, unless you can do like say something like a conditional breakpoint. So if you can break and then have some condition if some variable is such and such, and then you can use the reverse continue then to move back until that point. So I don't believe we have something that's specific to a line number at this point.
Okay, can you capture programs using external hardware, network devices, or GPU or FPGA accelerators? Yeah,
so our technology is kind of fixed to x86, x64, Linux distributions or Linux kernels. So there are some limitations there. We're not able to capture other instruction sets. So that would things like FPGAs or GPUs. What we have found is some customers are able to use UDB to understand how their application is communicating with those external accelerators. So you can see the data that's been sent to the accelerator, you can see the data that's been returned from the accelerator, even if you can't actually step through what that external hardware is doing in the meantime. So yeah, there is a limitation there, but in terms of a debug workflow, you can monitor inputs and outputs from those external hardware devices.
That's great, really comprehensive answer. And we've got a question here from Andreas. How about lock-free algorithms? Does serializing constrain the available interleavings, as it will likely flush CPU caches and therefore act like a memory barrier?
Without knowing the specifics of that, I don't believe so, because I think the serialization of threads really is only a problem, potentially a problem, when you have true parallelism, where you have something masking something else. So I don't have a good answer for that. My thinking was that it wouldn't be a problem, because I don't see how the serialization would necessarily cause sort of a different behavior. But without really drilling down into that, I don't think I can say one way or the other. Yeah.
Okay. Is there an estimate on the size of recording on project size or debugging info size? That's from Amit.
Ahmed, hi. So yeah, again, good question. The way that our recording works is a sort of two-step thing. Initially, we'll take a snapshot of memory, and then we will record each instruction as it's executed. So that allows us then to reproduce application state at any point in the history of that application. So there's a couple of things to note there. Obviously the memory size that the amount of memory that we take is going to be dependent on how big that initial snapshot is, and the size of that snapshot is going to be dependent on how big your application's memory footprint is. So that's one thing, and you don't really have a lot of control over that because it's really application specific. The second part, the event log, as we call it, the part that records all the changes, all the diffs that have occurred since that snapshot was taken. That's a circular buffer, a ring buffer, and it's configurable in terms of size. So you can determine how big or how small you want that to be. And the reason why that's important is, if you do find, for example, that the default setting is too small, and you are basically overwriting some of your previous history, then you can make that buffer bigger just to suit your needs. So there's a little bit of configuration, and you generally, what we find is developers get a better understanding through usage as to what sort of values they need. The default value we found in 95% of cases is definitely big enough. It's about 1 gig in size, I think. And just one other thing to say about that, although we're taking a snapshot, we're doing it using Linux's copy on write mechanism. So that snapshot is only going to be have useful information or as and when each memory location is touched by your application. So for the most part, it's going to be full of zeros. If you were to take the sort of pathological case, if your application was to touch every memory location that it has access to, then that's true. That's going to be a full size snapshot. But for in most cases, applications are only really touching specific parts of the memory address space, and the rest of it will be zeroed out. So we have two things. So one is we have this sort of strong compression capability, and also representation internally, sparse representation internally. So we're able to really optimize the memory footprint.
That's fantastic. So I think we have one more from Amit. That's great, thank you. Do I need to tie UDB to a process at the spawn time, or can it be triggered at some point during the execution? If so, can it be programmatically triggered? Great question.
Yeah, so the answer to that is certainly. I mean, just like GDB, you can attach UDB to a process at any point in that process's history, and there's some flexibility in terms of whether you start recording straight away or whether you let it run for a bit or whatever. So you don't have to start recording at the beginning. You can actually start recording at any point in your application's history. And of course, just like GDB, UDB is totally scriptable. So you can either use, you can use GDB command lists, for example, to get a bit more, some more sophisticated type sort of workflows within the debugger itself. But it's also completely scriptable via GDB's Python interface. So again, there's a lot of scope to do more complex workflows through Python scripting.
Fantastic. Do we have any more questions from the audience before we move on to the next section of the webinar? Okay, well, I'd like to say thank you very, very much. Thanks everyone for all the questions. Stuart, thank you so much for your presentation and run through. I think, oh, right, okay, Michael Winkler has a question, and yeah, I'm glad this has come up. Michael says, running UDB usually slows down the program by a factor of around 50. Can you talk about deferred recording a little bit?
Yeah, so there are going to be certain instructions which are going to be slower under recording than other instructions. Things like file IO can often be a little bit slower because file IO represents what we would term a non-deterministic instruction. I don't mean that in a threading sense. I mean just in the sense that we don't know what the value is going to be when it's returned. That's different to when we add two numbers together. We always know that the output of that instruction is always going to be deterministic. It's always going to be the same. But some instructions such as get time of day or what have you, or file IO, we don't know, and that's where we see some slowdown. So applications have different phases generally, and often you find that the initial phase is one where there's a lot of file IO while you load data into your application. So using deferred recording allows you to run full speed past that point. You can set a breakpoint after that phase of your application, and then at that point you can enable recording and get some decent performance from that point onwards. So yeah, using deferred recording and the urecord command is a good combination. It's a good way of optimizing your record time. Generally speaking, record times, we usually quote between 3 to 5 times. There are going to be some cases where it's more. There are often cases where it's less, and many of our customers are seeing much less than that. But it's all about really just making it work for your application and making sure that you understand what potentially the performance overhead might be for a particular part of your application, and then using some of the configurability or some of the flexibility within UDB to overcome or bypass or work around those situations.
So thank you very much on behalf of myself, Stuart, Chris Croft-White, and the team at Undo. Thank you.